please, at any time, if you do have questions, please jump onto the chat and ask your question, and I will answer them as best I can. We'll also allow some time at the end of our time together today to go through questions and answers. Our agenda is as follows. I want to talk just a little bit about 5G spectrum, a little bit about a couple of different deployment options, a non-standalone option as well as a standalone deployment option, a little bit on multi-access edge computing, and we'll conclude our time together talking about network slicing. Now, before we get into any of these 5G discussions, what I'd like to do is talk a little bit about just kind of the nature of data and the fact that the world as we know it is changing. We're wanting to have more and more broadband access in dense areas, be it a football stadium, soccer stadium, or a university campus. There's a demand to have more bandwidth so that we can do more video and photo sharing. We have a need for extreme real-time communications, especially if we start to think about manufacturing and robotics. We need to be able to make decisions and communicate that to a piece of equipment as quickly as possible. We have a desire to have broadband access everywhere, with a goal of over 50 megabits per second, even at the cell edge. And then lastly, we're having more and more deployment of Internet of Things. As a matter of fact, over the last couple of weeks, my wife has deployed an Internet of Things device, mainly to turn on a grow lamp for her orchids. So twice a day, the orchid's grow lamp turns on its own and turns off on its own. And so my wife is not the most technologically advanced. She's not an early adopter of things. But if we've hit the point where my wife is using Internet of Things technology, you know it's big. You know it's big. There's a need to have mobility even if we're using high-speed devices like commuter trains. Being able to do connectivity of drones while in flight. We need to have ultra-reliable communications for things like e-health, remote medical treatment. We also want to be able to support smaller bandwidth services that go to a wider area, broadcast-like services for news and information, as well as lifeline-type communications where we're dealing with things like natural disasters and emergencies. So the world as we know it is changing. What's going to help us facilitate some of those changes? And that's what we want to talk about today. So let's start with a discussion of 5G spectrum. With respect to 5G spectrum, there's a lot of different options around the world. And we can take this chart and we can draw a line right here. And on the left-hand side of this chart is what we typically refer to as sub-G, or I'm sorry, sub-6. And on the right-hand side of this, we typically refer to this as millimeter wave. Now, the significance is kind of twofold. One, there's a physics significance to this. The lower the spectrum, the better the coverage. So sub-6 seems to be a very desirable spectrum from that regard. I need fewer cell sites. It's able to travel farther. I'm going to have better cell coverage. I'm going to have better throughputs at the cell edge. Great, fantastic, wonderful. So sub-6 is what we've been dealing with for really the last 30 years of wireless in some form or fashion. We move to millimeter wave. Well, millimeter wave has a lot of negatives when it comes to the physics perspective, but one of the advantages that millimeter wave has is size. We have some bandwidths in some countries that are in upwards of 400 megahertz of bandwidth. Compare that to what we have in the sub-6, and it's just a complete different story. So how is it that we're able to get to such high throughputs with 5G? Well, one of the reasons is with millimeter wave, we just have that bandwidth available to us. We have the ability to do such a large amount of spectrum, a large amount of bandwidth. But there's a cost to that, and that cost is how far can the signal travel? Now, every country is going to do this slightly different. This is a chart that just kind of shows you high points across the world. But the key message here is there is a demand for higher and higher bands. On top of that, we're going not just supporting our normal licensed bands, we're also going to more of an unlicensed model. There's going to be more sharing of bands. So there's a lot more technology that's needed for those. If we're in that sub-6, we are typically referring to these as cellular bands. And with those cellular bands, as we've talked about, we have the ability to have a bigger cell site. For greater than 24 gigahertz, the millimeter wave, and we've got a couple of examples of 28 gigahertz and 39 gigahertz, what we're dealing with is those wider channels and shorter distance. But what do the higher frequencies really mean? Some of this we've talked about. Larger channel bandwidth available. Okay, cool, we love that. Smaller antennas also mean shorter wavelengths. What this is really getting at is we have another physics property, and that physics property has to do with the size of the antenna is related to the actual size of the wave, the radio frequency wave. The larger the signal, the larger the wave, the larger the antenna. And let me give you my favorite example, just a very practical, simple example. I was a disc jockey for a number of years when I was in college, and we had an AM radio station and we had an FM radio station. The AM radio station, the transmitter was the tower. The tower itself was the transmitter. It was a huge thing. You move to FM, the tower is, or the transmitter is still, the antenna is still very large, but it's still mounted at the top of the tower. It's smaller than the tower itself. So if you can imagine going from AM to FM, and now we're going from FM to 24, 28, 39 gigahertz, that antenna is getting smaller and smaller and smaller. So why is that valuable? Well, why that's valuable is that really leads us to the next point. The smaller the antenna is, the more antennas you can have. The more antennas that you have, that gives you the opportunity to do more and more MIMO. MIMO stands for multiple input, multiple output. And what I want you to think about with respect to MIMO is the fact that, in essence, the more antennas I have, the more signals I can send. The more signals I can send, the higher the capacity can be. And so this middle part is something else that's also very, very valuable with respect to that millimeter wave. But as we've already talked a little bit about, the big negative of millimeter wave is the shorter ranges due to that propagation loss. And so we're dealing with cell sites that have a radius going from tens of kilometers in the typical cellular bands down to hundreds of meters in the millimeter wave. And that's a huge, huge decrease. On top of it, since there's so many different types of services that are available to us, we need to make sure that we're designing our specific network based off of the needs of that area. Not every area is the same. We need to start asking some questions. Things like, what are our service requirements? What is the specific service that we're trying to provide? What resources are available in that particular area? What cell size do I want? If I'm dealing with a rural area, quite large. If I'm dealing with a suburban area or a downtown area, much smaller. Maybe I'm dealing with an industrial complex. Maybe I'm dealing with a university where you have a very large number of devices that need to be maintained. What is the transmit power that's needed? If you're dealing with a lot of very low power devices that are, sensors, maybe not much. What different antenna techniques do you need? And then lastly, what is the link budget that's needed for 5G? And if you're not familiar with the term link budget, a link budget is kind of like any budget. Imagine that I had some type of a ledger. And what that ledger is going to have is pluses and minuses. With a link budget, the pluses are going to include things like power. The minuses are going to include things like loss, interference. At the end of the day, I have to have a certain amount of power that reaches the mobile device, or in the converse direction, a certain amount of power that reaches the antenna, or I can't actually do anything on that cell. Kind of like if I do my budget at home and I don't have enough money left to pay my mortgage, I've got a problem. When we're dealing with that millimeter wave, because the power of the signal drops off so quickly, that can be a challenge. Okay, so part one. What are some of the 5G spectrum challenges? What's the 5G spectrum that's available to us? Part two. Let's look at a couple of deployment options. Now, as we go through the deployment options discussion, what I want you to do is I want you to think about this from the perspective of evolving to 5G. So there's really two kind of flavors that we can look at. We can look at kind of a new deployment. I've newly acquired spectrum and I want to deploy a wireless network for the first time, so I'm going to start with 5G. Okay, great, we'll look at that. But that's not the way most people are today. Some, but not everybody. Most people are going to evolve. They already have a 4G network, so then the question is, how do I move from a 4G network to a 5G network? So if I'm a new deployment, or we could refer to this as an overlay, I'm going to do something that's referred to as a standalone deployment, or SA. And what the SA deployment is saying is, this is a completely separated, different network. I have a 5G core network, I have a 5G radio network, and there is no relationship with the 4G network. It has its own set of protocols and interfaces. We can talk to the mobile, we can talk to the base station, and the base station is now referred to as a G node B or a GNB. So this is very similar to what we saw when we were evolving from 3G to 4G. We overlaid this 4G network. And we still had some ties back to 3G from time to time, but it was an overlay for the most part of the 4G network. But that's not what we see with a lot of people in the short term. In the short term, what we're seeing is some type of evolutionary approach, some type of dual support approach. So we see all the way on the right that standalone option. We see all the way on the left our 4G network. So one potential stepping stone is to do something called an NSA deployment, or a non-standalone deployment. And with this non-standalone deployment, what we have is we have a scenario where I'm going to go back, at least in this particular option that I'm showing on the screen, we're going to use our 4G core. And our 4G core is going to support both a 4G radio network as well as a 5G radio network. And what the mobile device will do was it will interface with the core network to figure out how it's supposed to receive data. Maybe I'm going to receive data over the 5G network. Maybe I'm going to receive data over the 4G network. And the mobile just does what it's told. All it does is says, hey, network, I've got the capability of supporting both a 3G, or I'm sorry, a 4G network as well as a 5G network. You tell me what you need. Now, over time, and I don't know how much time, but over time, even operators that are deploying this non-standalone will eventually start to move towards a scenario like we have on the right. If we can look back at history, what we saw was a dependence of the 4G network on 3G for a number of years. And then over time, they solved some problems. And now most devices, if you've got a modern device, this doesn't connect to a 3G network unless it can't find a 4G network. It'll only connect to the 3G network in very rare circumstances. I expect the same thing moving forward in this model. So what I showed on the previous graphic was one example of a non-standalone system, but there are multiple examples. So this is the one that we looked at a second ago, which is referred to as option 3X. We have another option, 7X, and in 7X, what we've done is we've evolved our core network to be a 5G core. So in other words, what we're saying is our 5G core will still support both 4G and 5G traffic. And then all the way on the right-hand side, this option 4, what we're saying is that we're going to continue to support the 5G network. We're going to continue to support the 4G network. But what we're going to do is we're going to have this G node B being our anchor point and everything flowing through that. And if it needs to go over and get the 4G node involved, great, we'll get it involved. If not, great, then we won't. And as we start to get to this option all the way on the right, we go even further. We're going to start to see that we're decommissioning that 4G network. So really our hope, just as what we've seen going from 2G to 3G and 3G to 4G, going from 4G to 5G, our hope is that we're going to start to, over time, have fewer and fewer mobiles that are 4G mobiles, and then finally get rid of our 4G network. But that's years and years and years before that's going to happen. Now, one of the other things I want you to see in this graphic, some of the icons that we chose at the top were very, very intentional. So notice when I'm talking about my 4G LTE network, I'm drawing an icon that looks like a stack of servers. And that's intentional. Our LTE network, for the most part, is being deployed as physical nodes. It's being deployed as physical nodes. Standalone nodes, monolithic pieces of equipment. The 5G core network has been designed to be much more virtualization friendly. So our view is once we move to having a real 5G core, they will be virtualized. Now I'm using the term virtualized to be generic here. They could be based off of virtual machines, or they could be based off of containers. That's not really the point of the discussion at this point. Really the point is that they're virtualized. And that's going to become very important as we start to look at a couple of other things that we want to talk about today. So let me pause for a second. Does anybody have any questions or comments? If so, please jump in the chat. I'd love to hear them. I want to make sure this is making sense. Because we've covered 2 of our 4 topics that we want to discuss today. Excellent. Now, the next 2 topics that we want to talk about, part of the value that they bring is a fundamental assumption that virtualization is a reality. If we've not deployed a virtualized network, if we don't have the ability to do what I refer to as workload placement, then these next two topics don't add any value. Now, all I mean by workload placement is the fact that I'm going to deploy a piece of software in the place that's most convenient for that piece of software. So for example, if I'm dealing with something that is very real-time sensitive or something that has a high bandwidth, I want to deploy that service not in a centralized cloud, but as close to the user, the subscriber, as possible. That's all I really mean by workload placement. What is the best place for the workload for this particular service? So the first topic we want to talk about is something called multi-access edge computing. In multi-access edge computing, we're starting to deploy resources more geographically close to where the subscribers are, where the mobile devices are. Now, why? Why is that an important thing? Well, some of this we've already looked at. We have a need for lower latency in real time. Now, one problem that we've not been able to solve in the last 120 years of telecommunications is the speed of light. I cannot go faster than the speed of light. So I will always have a delay equal to distance. So if I am trying to communicate to a server, and that server is 4 kilometers away, that's one set of delay. If that server is someplace else a few hundred kilometers away or 1,000 kilometers away, but it's still within the same country, depending on the country you're in, that's a different delay. I'm based in southern United States, and so if I'm trying to connect to a server that's in Sydney, Australia, well, that's a completely different amount of delay. And it doesn't matter. It doesn't matter the capabilities of the server, and it doesn't matter the service. The delay is going to be based off of that geographical distance. So as my need for lower latency in real time increases, I've got to move those resources to be closer to where the user is. Another thing is we're starting to see more and more bandwidth needs. And where we see this the most is in content. If I have a large number of people who are downloading the same file, watching the same video, having that content geographically close to where those people are is a huge savings. Now, one of the key advantages that most of our telecom operators have is they have a very large number of points of presence. So if you think about things over the last 50 years, especially when we had copper, the distance that a signal could travel across copper was much lower than the distance it can travel across fiber. And so typically what you had is you had a very large number of locations where you needed to have switching equipment for the sake of delivering basic phone calls. Now, as we move to fiber and we've modernized a lot of the equipment, I don't have as much need for equipment, but I still have those points of presence. Why can't I put something else in those points of presence? That's something that's very difficult for a competitor to do. That's something that's very difficult for a cloud provider to do. So that's another motivation for evolving our computing platform. A lot of devices have a very confined battery life. And so if I can offload any work off of that device, then I'm going to save the battery life. So that kind of pushes us back to the top half of this graphic. If I can take a service that was being run, it's a real-time sensitive service, and instead of running it on the device itself, running it on a piece of equipment that's nearby, then that's going to save battery of the device. We're also having a very large number of wearable devices. So I've got my smartwatch on as well. I've got a colleague who, and I don't understand exactly how it works, but he has, in essence, a smart ring. He's got a ring that he wears that will alert him to certain things with respect to body temperature, heart rate, and such. And so I'm very interested to what it does. The concept of the smart ring is kind of appealing to me. But my point is we have more and more of these types of devices. They're never going to have the battery life. They're never going to have the processing power to do a lot of this stuff. So all of these things together really point to trying to improve the user's quality of experience. So then what is MEC? MEC stands for Multi-Access Edge Computing. And just as the name implies, what we're going to do is we're going to deploy a server someplace that's geographically close to a cell site. Now, we're going to use terminology that's focused more on mobile networks, cell sites. But it doesn't have to be that. It could be I'm deploying a multi-access edge computing in an enterprise network. I'm in a multi-tenant building. That's where my office is. So why couldn't a service provider deploy a server in this building that's providing services for us? No reason why they couldn't. We're going to focus on it from a wireless perspective. In doing this, it's going to give us the ability to have improved user experience. All right, cool. The applications that are running are geographically close to the device that needs them. Security. So I'm going to have the ability to maybe do an extra level of encryption outside of this mobile access edge computing device. We'll have savings on transport. I'm only having to send my content a shorter distance versus sending the content from the core network. I can then start to do things like have more of a location-aware system. And then, as we've already talked about, offloading devices, offloading processing from devices themselves. One of my favorite examples of the offloading is with respect to a security camera. So let's just say, for the sake of argument, what we wanted to do is we wanted to have some artificial intelligence that's looking at the image and then alerting us if there's a problem. Well, building that into the security camera itself could be quite expensive. As a matter of fact, it's going to increase that cost quite a bit. Now you think, okay, so what? Maybe it's an extra $1 or $2 or $5 for a chip that goes into this camera. Imagine if I need to deploy 1,000 of those things. Imagine if I need to deploy 1,000,000 of those things. If I'm increasing this price by $5 and I've got to deploy 1,000 of them, $5,000. If I got to deploy 100,000 of them, it's $500,000 I'm spending. So that can get quite expensive quite quickly. So what I could do, if I could take this AI application, move it to my multi-access edge computing platform, now what I've done is I've got a cost savings on the device itself, and I've got an ability to still provide that service in a real-time fashion. We'll talk a little bit more about AI here in a little bit when we do our second presentation here in about an hour. So let's talk about a 5G network that's using MEC, using multi-access edge computing. So we've got our 5G core, and this 5G core is going to be located wherever a 5G core is located. And then we have the ability to deploy our edge computing function more geographically close to where that content is, where that subscriber is. Now, one of the other things, if there's anything we want to highlight on this slide from a 5G core perspective, it's this user plane function, or UPF. This user plane function is one of the things that I see a lot of people talking about moving to our multi-access edge computing platform. And that's going to provide many different benefits. Some could be nothing more than data is flowing from the mobile, it hits the user plane function, it goes straight out to the internet right away. It doesn't have to go all the way back to my core before it gets sent out. It can be offloaded very, very quickly. MEC, multi-access edge computing, is defined by ITU. In comparison to 5G being defined by 3GPP. And the only reason I bring that up is because I think it's interesting that they're the ones that are focused on this instead of 5G. And really the reason is because these were also the guys that did NFV. And if you're familiar with NFV, network functions virtualization, topic that's been kind of popular over the last 5 years or so, you'll see a lot of similarity. To me, there's a lot of overlap between those two concepts. If you're interested in learning more, you can always look at the ITU, as well as there are some open source initiatives that are starting to come about with respect to this. And one of those is something called openness. And this is something that Intel has pushed. So you can go to openness.org and you'll find out a little bit more about that. So let's see this in action. Let's see this in action. So I've got a mobile device, it's got the RAN, and I've deployed a UPF function for this mobile device. It has some things that are in a centralized data network, and so we can see he's getting to apps X or Y and Z. But he's also going to a MEC down here to get access to app X. And the reason that we're wanting to do this is so that we can have a faster turnaround for that particular application. Another option that we can have is to also do what's referred to as a local area data network. And with a local area data network, it's allowing us to offload traffic very, very quickly. And this is going to improve our performance. We're going to carry less traffic in our network. And that's going to also just speed up everything. So if we think about the MEC use cases, there's a number of use cases that are very, very valuable for MEC. And there's some that are going to come about over the next few years, but these are the ones that are talked about the most. Connected vehicles. Somehow allowing us to send large quantities of data to some type of server so that can be shared with other connected vehicles. This is referred to within the connected car space as V2X, vehicular to whatever. I might put some video analytics in this. With video analytics, what this is allowing us to do is to take our video traffic that we're trying to send, and we can analyze it to some degree. Or it could take video that we're trying to watch and analyze it and try to do more intelligent things. So for example, based off of the content that I'm watching, it may push a different type of advertisement. Factory automation, we talked a little bit about that. That's really more of that real-time sensitivity. And one of my favorite discussion is to talk about augmented reality and virtual reality. Now, the reason augmented reality and virtual reality is such an important concept for something like the multi-access edge computing is really twofold. One, I want to get away from having a tethered device. I could put on a headset and have the headset tied to my laptop. That's fine. But the problem with that is that I have very little mobility. What I want to be able to do is I want to be able to have a tetheredless solution and have something nearby that's rendering the graphics and sending it to my device. Now, the other piece to that is there is something called a photon to motion latency. Photon to motion latency. And what this photon to motion latency is saying is, imagine you've got this headset on, a virtual reality headset. And as I turn my head, does the image turn with me? What is the delay that my brain can handle? And if you've ever heard of VR sickness, That's really what VR sickness is all about. It's the fact that your body is physically moving, but what it's seeing isn't changing fast enough. And there is a part of your brain, and I can't remember the name of it off the top of my head, but there's a part of your brain that just gets messed up. And that can cause you to be physically sick from that. So this photon to motion latency needs to be less than 20 milliseconds. So in other words, when I turn my head, the image has to change, has to match within 20 milliseconds. If it doesn't, we have a problem. When we start looking at augmented reality, that delay gets even lower. It gets to around 10 milliseconds. And the reason is because of that. Imagine I've got my smartphone, and my smartphone has, I'm in a major city, and so I've got the camera going, and what it's doing is it's superimposing on that picture information, maybe what you'd find like in Yelp. There's a restaurant over there to the right. It's a Korean restaurant. You over here, oh, this is an Indian restaurant over here. And oh, over there is whatever. Now, the problem is as I move my phone, the image moves because it's a real image. It's coming from the camera. Does the overlay move at the same pace? If the overlay moves late, then that augmented reality can be off center, and that can cause it to give false information. So those are some key use cases within MEC. Okay, we've covered 3 of our 4 topics for today. Spectrum, we need a lot of it. We're getting it from this millimeter wave, which has some positives and negatives. We're evolving to 5G, so we're probably, in most cases, not deploying a standalone system. We're deploying a non-standalone system, something that's going to allow us to have a support of our 4G network as well as our 5G network in some forms. 3, we want to be able to support a network placement so that we can put a service geographically close to the subscriber based on his needs. If he doesn't have that need, if you're just doing basic web surfing, I don't necessarily need to do that. I might want to go the conventional way of going up to the core network because it doesn't buy me anything otherwise. Our last topic that we want to talk about is network slicing. And network slicing is building upon a couple of concepts we've already talked about. The first piece of network slicing that's very critical is to talk about things like MEC. We're going to be using MEC concepts as part of network slicing. And the second thing we've talked a little bit about is virtualization. And so let's get into network slicing. So what is the concept of a network slice? Well, just as the name implies, what we're trying to do is we're trying to share our end-to-end network. We're trying to divide it up so that we can have an end-to-end quality of service. And the key piece to this is end-to-end. So we're not talking about sharing the air interface. We're not talking about trying to set up some resources in the air interface. What we're trying to do is we're trying to set up resources end-to-end. So that's going to include the air interface, it's going to include our transport network, and it's also going to include our core network. How can we set up a slice of all of those resources to make them available for one particular type of service or one particular type of device? Some standard slices we can think about is we can have enhanced mobile broadband. We can have massive machine type communication, and we can have ultra reliable, low latency connections. So you can imagine, depending on the type of service that your device is trying to do, I may say, I need high bandwidth, or I need low latency, or this is a factory, and so I need more of the machine type communication. So that's a network slice. So as we've already talked a little bit about, what we're talking about doing is trying to divide all of these concepts and kind of divide them up so that a service or a subscriber or a type of device can access them. So in this particular case, I'm defining 3 types of network slices. I've got one for my mobile broadband, just the average subscriber doing its normal web surfing stuff. I've got one for my vehicular to X, my vehicular communication, and I've got one for IoT. Now, when I define that network slice, I'm not just saying, oh, I want this type of service. What I'm saying is, no, no, no. We're going to define a slice, and we're going to say that slice includes some chunk of radio resources, and it's going to include some chunk of core network resources, and it's going to include some chunk of transport network resources. Same with V2X, same with IoT. So this is implying, kind of the way this slide is drawn, it's implying kind of 3 different networks. I don't want to have that. It's one network that we're logically dividing into 3 networks. So this is really my RAN network. This is really my core network. But I'm dividing them into these different sections based off of their needs. Now, the air interface, we've been doing that for a long time. We can go back into the 3G era, and we've have the ability to do quality of service over the air interface. Definitely within 4G. The air interface could support VoLTE, which requires a certain level of quality of service in comparison to basic web surfing. Now what we're talking about is saying, no, 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 I don't want to just focus on the air interface. I want to focus on this end-to-end. So the transport network, as well as the core network. So some of the benefits of this. Well, the first benefit is this is going to allow us to provide more and more different types of services. We can be more and more ingenious and provide more value-added services to the clients, to the different subscribers. This is going to allow us to have a better revenue as well as to better manage our network resources. One of my favorite examples of this, we talk a lot about this from a service perspective. I'm doing like broadband versus IoT, which is a great use case. I'm not knocking that use case, but the use case that kind of excites me in this is things like an MVNO. So we've been doing this mobile virtual network operator for years. But now what I can start to do is they can have their own slice. So one slice can be dedicated to an MVNO. And so now, if I'm an operator, I'm just giving them that slice and they're managing everything else. I'm not having to deal with separation of traffic. Hey, you want that MVNO slice? Great, go for it. They have to manage all of that stuff themselves. As well as this allows us to monitor and kind of partition our resources better. We can develop new business models. We've kind of talked a little bit about that with respect to the MVNO. And then lastly, it just gives us the ability to separate our network into multiple slices so we can manage each of those slices better. We're not having to worry about one service starving the rest of our network. So one of the things that has been said about 5G for a few years now, in comparison to 4G and 3G, is 5G is much more service-centric. How can I provide services to subscribers? It's not bandwidth. It's not connectivity. It's services. It's services. So we've talked about some of this, but what are some of the different potential use cases? We've talked about kind of splitting my network based off of the demands of the service. Is it broadband versus low latency versus machine-to-machine type communication? Maybe it's going to be based off of level of service. Are you paying the gold service, the bronze service, or the silver service? Now, we haven't seen this in the wireless space yet, but we do see people making decisions on the type of connection they get to their home, their broadband connection at home, based off of things like, can I pay more to get a better latency? And this is really that gaming community. I've had friends who would change who their internet service provider is because the latency was so bad and they couldn't play their game sufficiently. We could do slices based off of things like voice slice and a data slice and a video slice. Market segments, MVNOs we've talked a little bit about, as well as business versus consumer. If I've got a consumer or a business solution, I want to make sure my business solution isn't starved by my consumers in a certain area. I could definitely see that in kind of a college type area where what I might do is have kind of classes of service for the faculty in comparison to the students. So in my mind, one of the big keys to supporting network slicing is virtualization and orchestration. And when we talk about virtualization, we really need to think about both virtualization from a computing standpoint as well as from a network standpoint. And that network part is the part that I am to some degree concerned about, because we haven't done a good job of that in practice. We're starting to get there. We're starting to see more of that, but that's still an area that we could do a better job of. So what is the end-to-end framework for network slicing? Well, we need to define slices. That's really what we're talking about in this upper left-hand corner. We're defining the slices from a radio network perspective, and we're defining slices from a core network perspective. We also need to be able to define slices from a transport network perspective. This might be using things like MPLS to manage that. This might be just using simpler SDN concepts or SD-WAN concepts. But making sure we have the ability to partition our transport network for that separation. I don't want a huge rush of one type of service to cause problems with another type of service. But the other thing that we need to make sure that we're not losing sight of is the fact that we need some type of management network for the slicing. We need to be able to define these and communicate them to the mobile. We need the mobile to be able to request a specific slice that they want for their specific service. The mobile needs to get approval for that. So we need network slice management, as well as communication of the different services that are available. So one last concept before we wrap things up for today. Network slicing isn't just a network concept. It goes all the way down to the mobile device itself. So the mobile device is going to have lists of networks that they can connect to. It's going to be able to identify those networks based off some information that's on broadcast channels. And it's going to be able to communicate what it needs as part of an attach, as part of a registration, as part of a connection. So let me pause there. Before I do my last little wrap up, any questions, comments, thoughts based off what we've talked about for the last hour? All right, fantastic, fantastic. So 5G spectrum includes both sub-6 as well as millimeter wave. And we talked a little bit about kind of the advantages of both. We could deploy a non-standalone as well as standalone options for 5G. The most widely considered early adopter of the non-standalone is that option 3X, where we have the LTE core connecting to both 5G and 4G RAN. MEC really gives us the ability to do that workload placement, and network slicing allows us to do more of an end-to-end partitioning of our resources. Fantastic. So, any last-minute questions before we wrap things up? I want to thank everybody for taking time out today and spending time with me to talk about this. Thank you for being a part of this. If you were part of the discussion that we had in Los Angeles, thank you for coming back. Here in 30 minutes, 35 minutes at 2:30 Central Standard Time, we're going to do part 2 of the presentation that we did in Los Angeles, which is on jump-starting your team's machine learning journey. Please feel free to come back for that if you're interested. Other than that, thank you guys so much. I really appreciate it. Have a great Christmas break, and I hope to work with you again in 2020. Take care.